Welcome to this video. Today I'm going to do this practice gas laws for y'all. I'm only going to do the odds, that way you can go back and do all of the evens. So if you look at this first part where it says the directions, yes, we have to read directions. Number one, I want you to label all known and unknown variables so that way we can identify, one, what we need to find, and two, we can identify what law we're using. All right, y'all remember that foldable we just made with the different gas laws? We're going to be using that to help us out here. Also, you need to make sure you show all of your work for credit in order to get the final answer. Because I'm doing the no work, no credit. Don't show your work. Oh, well. All right, starting with number one. I am going to label everything in this problem. So very first thing is a 3-liter container. Anything that has liters is going to be volume. All right. So particularly, I'm going to put V1, volume 1. A 3-liter container of hydrogen gas has a pressure of 4.4 atm. So obviously this tells us this is pressure. We're going to put pressure 1. Now, what is the volume, or what volume? So we're looking for a second volume. I'm going to label that as V2. Would be needed to decrease the pressure to 2 atmospheric units. So, and we're looking for, or they're giving us P2. So here we have two things. We're dealing with volume and we're dealing with pressure. The only law that lets us use volume and pressure is Boyle's law. So make sure you label what law you're using. Boyle's law. The formula is going to look like this. It's going to look like P1, V1 is equal to P2 and V2. And if we label what we already found some of these things. We know we found V1. V1 is 3.0 liters. P1 is 4.4 atm. We are looking for V2. But we know that P2 is 2. So I'm looking for this here. Oh, excuse me. So let's go ahead. First, let's rearrange this equation in order to find V2 by itself. So we should have P1 V1 equals P2 V2. We need to get V2 by itself, but P2 is right next to it, so I need to move that P2 over. Now, P2 and V2 are multiplied by each other, and the opposite of multiplying is dividing. So I have to divide, and whatever you do to one side, you have to do to both sides. I have to divide both sides by P2. And so our final equation for V2 is going to be P1, V1 all over P2. And if I can plug in each of these over here into this equation, P1 is 4.4, V1 is 3.0, P2 is 2.0. So plugging that in, now let's go ahead and pull up our calculator. All right, so let's go ahead and type this in. 4.4 times 3.0 divided by 2.0. And this gives us a total of 6.6 And we're looking for volume, so liters. And that is your answer. So again, label what you know and what you don't know. Number 2, identify what law you're using so that way you can figure out what equation you're using. Let's go ahead and try out number 3. Consider a 910 milliliter. So milliliters, that would be volume, right? Because liters are volume, milliliters are also volume. So we're going to label this as our V1. So consider a 910 milliliter of carbon dioxide at 28 degrees Celsius. Celsius would be temperature. If the temperature is increased to 49, so this is our second temperature, what will the volume be now? So we are going to be looking for V2. So labeling what we have, we know that V1 is 910 milliliters. T1 is 28 degrees Celsius. T2 is 49.1 degrees Celsius. And we are looking for V2. All right, so the thing about this, we have our temperatures in Celsius, and no matter what, our temperatures cannot be in Celsius, no matter which law, they have to be in Kelvin. So in order to go from Celsius to Kelvin, we are going to add 273.15 to both of these. And that'll put our temperatures in Kelvin. So 28 plus 273.15 is 301.15 degrees Kelvin. All right, so now that we know we're only dealing with volume and temperature, volume and temperature is going to be Charles's law. And Charles's law is V1 over T1 is equal to V2 over T2. So, and we are looking for V2 here. So V2 is on top. That means we need to get this T2 away off of the bottom. We only want V2 by itself. Now, in order to do that, I'm going to do the opposite of what the formula is. So right now, T2 is being divided. Let's do the opposite of that and multiply by T2 on both sides. So this would cancel out, and we are left with V2. We would have T2 times V1 all over T1. So this will be our equation we're using now. And we can go ahead and plug in those numbers. So our T2 was 322.25. Our V1 is 910. And our T1 is 301.15 Kelvin. And if we plug all of this in to our calculator, 322.25 times 910 divided by 301.15, we get 973.76 milliliters. Because we're looking for volume again. Right? First volume was in milliliters. That means volume 2 has to be in milliliters as well. Anyways, that's how we do the first couple of problems. Let's go on to number 5. So number 5, if containers with 3 different gas samples with pressures of 2, 3, and 4. So we have 3 different pressures here. We have P1, P2, and P3. Are combined, what would be the total pressure? So looking at your foldable, the law that talks about total pressure would be Dalton's law. And Dalton's law is whenever you have a total pressure, that is equivalent to all of your partial pressures summed up or added up. So we have our total pressure, which is what we're going to be looking for, and that is all of our partial pressures added up here. So we can just plug each of those in, 2.0, 3.0, and 4.0. That means our total pressure, once we add up 2 plus 3 plus 4, so 2 plus 3 plus 4 is a total of 9 ATMs, or atmospheric pressures. So this one was pretty easy. Number 7, a gas in a closed container is pressurized from 10 ATMs to 20. So this would be our first pressure, P1, and P2, because it's going from 10 up to 20. Now, if the original temperature of the gas was 28 degrees Celsius, what would the final temperature be? So we're looking for T2. Now, listing out what we have so far, we know P1 is 10, P2 is 20, T1 is 28, and T2 is what we're looking for here. Now, no matter what, this is in degrees Celsius. And what do we need it to be in? Kelvin. So we have to go ahead and add 273.15 degrees to that. And that will give us a total of 28 plus 273.15, 301.15 degrees Kelvin. All right. We have our knowns. Now, this law, we have pressure and temperature. The only law that has both pressure and temperature would be Guy-Lussac's law. All right, Guy-Lussac's law is P1 over T1 is equal to P2 over T2. And if we're looking for the final temperature, so T2, let's go ahead and figure this out. Well, first, I cannot do anything with T2 on the bottom. Let's get T2 on the top. So instead of being divided, let's multiply both sides by T2. So that will get rid of T2 here. Then we would have T2 times P1 over T1 is equal to P2. Now, we still don't have T2 by itself, so we have to do the opposite of this fraction. So instead of P1 being on top and T1 being on the bottom, let's flip it. Let's multiply this by T1 over P1 on both sides. So that way our new formula will look like this. I'll write it up top. T2 is equal to P2 times T1 all over P1. And that will be our new formula here. And if we can go ahead and plug in what we have so far, we know P2 is 20. T1 is 301.15. And P1 is 10. Plugging that in, our second temperature will be 20 times 301.15 divided by 10, which is 602 Kelvin. Because we're looking for temperature. Temperature has to be in Kelvin. All right, so that's question number 7. Last one, let's do question number 9. Consider a gas with a volume of, so we're looking for volume here, 700 milliliters at an atmospheric temperature and pressure. So, atmospheric temperature and pressure, that would be just standard temperature and pressure. And standard temperature is 273 Kelvin. Standard pressure is just 1 atmospheric unit. All right. What would its new volume be? So we're going to be looking for volume. All right. And it's also giving, so this is our second volume. This is our second temperature. And this is our second pressure. I was confused for a second. All right. So we have V1, T1, P1. And we're looking for V2. So V1 is 700. V2, we don't know. T1 is 273 Kelvin. T2 is 405 Kelvin. P1 is 1 atmospheric unit. P2 is 1.85 atmospheric units. Now, we have 2 sets of everything, and the only law that gives us 2 sets of everything would be the combined gas law. And that would be P1 V1 all over T1 equal to P2 V2 all over T2. Let's go ahead and plug in our formula or our values here. So P1, V1, and T1. We know those are 700 for V1. P1 is 1. T1 is 273 Kelvin. P2 is 1.85. V2 is what we're looking for. T2 is 405. All right, so how do I solve this part? This is going to be a little bit tricky, but it's really not that bad. First, let's go ahead and plug in all of this side into our calculator. Let's see what we get over here. So we get 1 times 700 divided by 273, which is, I'm going to round it to 2 decimal places, 2.56. Now, let's do the same thing with these numbers. Now, we don't know what T2 is. That's okay. But we can at least find this part, 1.85 divided by 405. 0.005. I'm put T2. No, it wasn't T2, it's V2. Now I have V2 and I need to get rid of 0.005. So let's go ahead and divide on that by that on both sides. That way, our answer, we get V2 is equal to 2.56 divided by 0.005. And we get 512. What is this, milliliters? Yeah, milliliters. And there we go. There's your answer. So onto the back side of the ideal gas law. So here, this entire page, you're going to be using the same law, which is the ideal gas law. So starting with number 1, what is the pressure? So we're looking for pressure when we have an 8.75 liter, so that's a volume container, with 1.54 moles in, and at 307 Kelvin, so that would be our temperature. So we don't know what pressure is, but we know volume is 8.75. Number of moles, 1.54. Temperature is 307. And one other variable that we have not touched yet is R. Now, R is the ideal gas constant. And this is 0.0821. And you're going to use this every single time you have an ideal gas problem. So the ideal gas equation is PV is equal to nRT. Now here, we're going to be looking for P. So let's go ahead and get rid of V on this side. So our equation would be nRT all over V. And if we plug in what we know here into each of these spots, we know that N is 1.54, R is 0.0821, temperature is 307, volume is 8.75. And using our calculator to plug this in, we have 1.54 times 0.0821 times 307 divided by 8.75 is a total of 4.44 ATMs, atmospheric units, because this is in pressure. Okay, now number 2 is going to be a lot like this. Let's go ahead and do number 5. How about that? So temperature here, anytime you do temperature, it always has to be in Kelvin, just so you know. So number 5, what is the temperature? So we're looking for T with 15 grams. Ooh, so this is grams. They're giving us mass or M. We don't need to find M. We need to find N, which is our number of moles. So we're going to do something a little bit different in this problem. So they're giving us 15 grams of hydrogen gas. Hydrogen gas is H2. At a pressure of 1.25 atmospheric units in a 20-liter tank. So we do not know what temperature is, but we know that our mass is 15 grams. We don't know the number of moles. We do know pressure is 1.25. Volume is 20 liters. And we know what our rate All right. Our rate for the ideal gas law never changes. It's 0.0821. So, we know the ideal gas law looks like this. We are going to be looking for temperature. So in order to do that, we needed to get rid of N and R on both sides. That way T is by itself. We get pressure and volume on top of number of moles and our gas constant. So this would be our formula we're using. However, we still don't know N. N would be our number of moles. But we know this is hydrogen gas. We know the mass. We just need to find the number of moles. So let's go ahead and find molar mass. This is a flashback to the last unit. So molar mass of H2 means we need to find the weight of hydrogen, and particularly there's two of them. And so the weight of hydrogen gas is 2.016 grams per mole. So now that we know the molar mass, right, we can turn 15 grams into moles. So setting up a table for our number of moles, we are given 15 grams in this problem. We know whatever's on top, same thing goes on the bottom. So if I have grams here, I need grams here, and we're going to change that into 1 mole. Now here we have top and bottom, so we need to divide 15 by 2.016. And that is 7.44 moles of hydrogen gas. Now that we know how many moles we have, 7.44, we have everything we need in order to plug it into our formula. So finally, our formula, we need to find temperature. We're going to be plugging in pressure and volume on top. Our pressure is 1.25. Our volume was 20. And we're going to divide that by the number of moles, which we found was here, 7.44 times our rate, 0.0821. So plugging all of this in our calculator here, we're going to get 1.25 times 20. Divide that by the bottom, 7.44 times 0.0821. And that gives us a total of 40.9. And since this is in temperature, this is Kelvin. So that is how you do number 5. So this one was a little bit different because they did give you moles, right? They did give us a grams instead of moles. So we had to find that number of moles. All right, let's go ahead and let's go to number 8. And this will be the last problem we do together. Actually, let's do number 9. So number 9, we have to find the mass. So this one's telling us to find grams, okay? We have to find grams, even though we have grams nowhere in our formula. That's okay, though. Of a 1.6 liter, so that's our volume, sample of methane gas, CH4, at STP. STP stands for standard temperature and pressure. So we know all of our different properties. We know that we have V, which is our volume. 1.6. Standard temperature. Temperature is going to be 273 degrees Kelvin. Pressure is going to be 1 atmospheric unit. The only thing we don't know is our number of moles, because we have to find moles in order to find grams. Okay, we know these are what we do know and don't know, what we need to find. Before we can do that anything, we need to know what is our formula. So here, we're going to be looking for N in order to find number of grams. So we need to get N by itself. So let's go ahead and divide by R and T on both sides. That way, number of moles is equal to pressure times volume over our ratio or rate and temperature, which I forgot to label over here. Our rate of the ideal gas is 0.0821. Anyways, all right, so we know for this problem, N is equal to P, pressure, which is 1, times volume, which is 1.6, divided by rate, which is 0.0821, times temperature, which is 273. So plugging this in exactly like this into the calculator, you will get a total of 0.0714 moles. So, and that's going to be your N. Your N stands for number of moles of CH4 in this problem. However, we cannot stop here. We do not need moles. We need to find grams, mass. In order to do that, to go from moles to mass, we have to find the molar mass of CH4. So the weight of carbon is 12.01, and 4 times the weight of hydrogen is 1.008. Plugging that in, we get 16.04 grams for every 1 mole. All right, so now we know the molar mass. We just have to figure out for every 0.07 moles, what is the mass? So our final thing, finding the mass, we know in this problem, we just found 0.0714 moles. And for every 1 mole, we get 16.04 grams. So multiplying straight across, we've done this before. We will plug in this straight across, 0.0714 times 16.04, 1.15. Round it, 1.15 grams of CH4. And that is your answer. All right, so that is the last problem I'm doing on this ideal gas page. That is it. Have a good day.